The enigma of uncertainty, when the entire universe trembles because of one tiny particle. Imagine that you are holding a simple ping-pong ball in your hand and gently tossing it upward into the air. You can predict with absolute certainty that it will fall back down and land precisely in the palm of your hand after exactly 1.5 seconds. This is the comfortable and predictable world described by Isaac Newton, where every object has a definite position, a measurable velocity, and a future that can be calculated in advance with perfect accuracy. Think about your motorcycle riding smoothly through a busy intersection, with your GPS device calmly announcing that you have exactly 800 meters to go before turning left, delivering that information down to the very second. Or picture your household cat curled up peacefully on the living room sofa, with a velocity of 0 and a position that remains completely fixed and unchanging. There is something deeply reassuring about this kind of order and predictability in everyday life. But now, let us shrink our perspective dramatically, far smaller than a grain of sand, tinier than the smallest bacterium, even smaller than the wavelengths of visible light that allow us to see the world around us. We have entered the mysterious realm inside a single atom. Here, everything suddenly transforms into a hazy fog of possibilities. An electron does not simply stand still in one spot or move along a straight and predictable path. Instead, it spreads out diffusely, much like the warm and inviting aroma of freshly baked bread wafting through a cozy kitchen on an early morning. You can sense its presence everywhere at once, but you cannot point to any exact location and say with certainty that this is precisely where it is right now. Scientists refer to this cloudy distribution as a wave function. This wave function pulsates and undulates gently, sometimes expanding outward and sometimes contracting inward, providing us with nothing more than probabilities. There is a 30% chance that the electron is currently located in the left corner of its imaginary container, a 55% chance that it is in the right corner, and the remaining 15% scattered diffusely like specks of dust dancing in a beam of sunlight filtering through a window. It was in the year 1927 when Werner Heisenberg sat alone in a small, chilly attic room in Germany. He clutched a cup of tea that had long since grown cold and stared out the window at a landscape blanketed in thick snow. Suddenly, he exclaimed to himself, "It is impossible to know both the exact position and the exact velocity of a particle at the same exact moment. To observe an electron clearly, one must shine a very intense beam of light directly onto it. That powerful beam strikes the electron with a sharp impact, causing it to jolt suddenly and change its velocity in an instant. On the other hand, if you attempt a more delicate approach by using a much weaker and gentler light, the electron merely vibrates slightly without much disturbance, but its position becomes blurred and indistinct, like trying to see through a thick morning mist. The chilling conclusion is this: the more precisely you determine where the electron is, the less you can know about how fast it is moving, and vice versa. This is the famous uncertainty principle, and it is not a limitation caused by imperfect measuring instruments or inadequate technology. Rather, it is a fundamental rule imposed by nature itself, an inherent property of the universe at its most basic level. Let us engage in a little thought experiment together to illustrate this idea more vividly. Suppose I possess a special box made from an advanced cosmic alloy, one that can be shrunk to any desired size with the simple press of a button. I carefully place a single electron inside this box while it is resting peacefully. I press the first button, and the box instantly reduces in size to that of a single grain of rice. The electron immediately reacts with alarm, beginning to race around frantically and bouncing off the inner walls with sharp, repetitive sounds reminiscent of hailstones pelting against a metal roof. I press the second button, shrinking the box further to the size of a small bean. Now the electron behaves like a desperate moth trapped inside a glass jar, colliding widely with the sides in every direction, and its energy level surges dramatically as a result of this confinement. Finally, I press the third button, compressing the box to an astonishingly tiny scale of 1/1000th of a millimeter. Suddenly, with a soft whoosh, the electron vanishes entirely, tunneling straight through the seemingly impenetrable metal walls and leaving behind only a faint, echoing ring like the sound of a delicate bell cracking. It has just performed a remarkable quantum tunnel jump, escaping from its prison without any need for a key or an opening. Where does this extraordinary burst of energy come from in such a confined space? Consider a scenario where you urgently need $10 million in cash. The banks refuse your request, and your friends remain silent and unhelpful. In desperation, you wander into a dark alley and encounter what we might call the cosmic equivalent of underground lenders. They offer you the money immediately, with no interest charges and no strict repayment deadline, but with one absolute condition: you must repay the full amount exactly when the time comes. The electron operates under a similar arrangement. It borrows energy directly from the vacuum of empty space. Contrary to what we might intuitively think, the vacuum is not truly empty at all. It is a seething cauldron bubbling with billions upon billions of virtual particle-antiparticle pairs that spontaneously appear and then annihilate each other in the briefest fractions of a second. The electron temporarily borrows a small portion of this fluctuating energy, uses it to propel itself forward or to tunnel through barriers, and then repays every last bit without missing even a single electron volt. The rapid crackling sounds you might imagine hearing are the auditory echoes of these ultra-fast cosmic transactions taking place all around us. Time itself is also bound tightly by the chains of uncertainty. A physical event or process that lasts for only 1/1000th of a second will exhibit energy fluctuations that can be enormous, potentially reaching millions of electron volts in magnitude. In contrast, a phenomenon that persists for many hours will have energy variations limited to just a few electron volts. This relationship mirrors the rules of our metaphorical cosmic lending system. If you borrow the energy for a very short period, such as one day, you can access vast sums, perhaps even billions, but if you borrow it for an extended period, like a full year, you are restricted to mere pocket change. The great physicist Albert Einstein once paced the hallways of Princeton University, shaking his head in disagreement and declaring that God does not play dice with the universe. He firmly believed that electrons must possess definite positions and velocities at all times, and that our inability to measure them simultaneously was simply a matter of not yet discovering the right experimental methods. However, nearly 100 years later, every single experiment conducted on Earth has unanimously confirmed that Heisenberg was correct, providing overwhelming evidence in support of quantum uncertainty. In the most recent developments, just yesterday at the Argonne National Laboratory in the United States, scientists achieved a groundbreaking feat by effectively freezing an electron in place within an ultra-pure diamond crystal. Using laser pulses that last for 1/4,000,000th of a second, they captured a precise snapshot of the exact moment when the electron leaped from one orbital path to another. The probability cloud surrounding the electron vibrated and shifted exactly as predicted by the wave function, with an accuracy deviation of less than 1 part in a trillion. Even more exciting news arrived a mere 3 hours ago from the CERN facility in Switzerland. The Large Hadron Collider, the world's most powerful particle accelerator, detected a solitary quark briefly escaping from the confines of a proton for a duration of 1/4,000,000th of a second. The energy borrowed from the vacuum during this fleeting event reached an impressive 230 gigaelectronvolts before being repaid in full without any residue. The researchers embraced one another in the corridors, hailing this observation as living proof of the quantum borrowing mechanism in action. Now, let us venture deeper into the fascinating domain of quantum field theory. The universe is no longer envisioned as a collection of solid billiard balls rolling across a smooth table surface. Instead, it resembles an immense fishing net stretched across the cosmos. Each intersection point in the net represents a fundamental particle, but the net itself is never still or static. It vibrates continuously, it sways and oscillates, and it even produces harmonious tones. Every single vibration within this vast network corresponds to a quantum field. There is the electron field, the photon field that carries light and electromagnetic forces, the gluon field that binds quarks together inside protons and neutrons, and many others. In Japan, the dedicated physicist Toichiro Kinoshita devoted a remarkable 35 years of his career to this pursuit. He filled thousands upon thousands of pages with intricate calculations by hand before transitioning to supercomputers, all for the purpose of determining a single extraordinarily precise value, the anomalous magnetic moment of the electron. The final result carried an error margin of just 1 part in a trillion, a level of precision so profound that it moved fellow scientists to tears in the laboratory hallways. In the year 1979, the Nobel Prize in Physics was awarded to 3 pioneering theorists who successfully unified the electromagnetic force with the weak nuclear force into a single framework known as the electroweak interaction. This achievement marked the first time humanity witnessed 2 of the 4 fundamental forces of nature dancing together in perfect harmony. Yet, the force of gravity continues to stand apart, aloof and unyielding, refusing to join the unification party. Picture empty space as a vast sheet of pure white silk laid out flat and smooth across an infinite plane. When a massive star passes by, the silk dips and curves inward, creating a gravitational well, and nearby planets roll along these curved pathways as if following natural tracks. This elegant description comes from Einstein's general theory of relativity. However, if you were to take a supremely powerful magnifying glass and zoom in on that silk fabric to a scale of 1/4,000,000th of a millimeter, what would you observe? Foam, an endless sea of tiny bubbles constantly forming, popping, and churning with violent energy. The physicist John Wheeler coined the term quantum foam to describe this turbulent microstructure of space-time. The bubbling and gurgling sounds you might hear in your mind are the actual noises of space itself boiling at the quantum level. At the incredibly minuscule Planck length, which measures approximately 1.61 times 10 to the power of -35 meters, the laws of physics as we know them begin to break down completely. The strength of gravity suddenly skyrockets to an unimaginable 1.21 times 10 to the power of 44 newtons, a force billions upon billions of times greater than the surface gravity of a neutron star. Physicists can only shake their heads in bewilderment and admit that conventional mathematics fails utterly at this scale. Currently, 2 promising theoretical pathways shine brightly on the horizon, offering hope for reconciling quantum mechanics with gravity. The first is string theory, which proposes that every fundamental particle is actually a minuscule vibrating string, and the different modes of vibration give rise to all the diverse particles and forces we observe. The second is loop quantum gravity, which envisions spacetime as an intricate web woven from tiny interlocking loops. Both approaches hold the exciting promise of finally allowing Einstein's deterministic worldview and Heisenberg's probabilistic realm to shake hands and coexist peacefully. In the meantime, as we await further breakthroughs, always keep this in mind: with every breath you take, billions upon billions of electrons are dancing wildly inside your body in accordance with the uncertainty principle. Every ray of sunlight that gently touches your skin consists of photons that have just borrowed energy from the fluctuating vacuum and are now repaying it. Even the very ground beneath your feet is frothing with quantum foam, live with incessant activity. Everything in the universe vibrates with energy, everything pulses with life and possibility. The story of the smallest particle has guided us all the way to the outermost boundaries of the largest cosmic structures. And perhaps, it is precisely this element of uncertainty that imbues reality with its profound beauty and wonder. Until we meet again to listen together to the subtle harmonies produced by the vibrating strings of the cosmos, I wish you a peaceful night of restful sleep, and may your dreams be allowed to remain delightfully uncertain, full of endless potential and surprise.